Okay, um, so let's get started, guys. I just want to go over. This is the exam review that was supposed to be in class, but this is kind of covering higher order regression with n parameters. So really, I mean, this is symbolic regression, cubic, quadratic, and then some other things that Dr. Miller had asked to go over were ordinal and categorical data. So I'm going to cover those as well. Um, so I figured we could start with the ordinal and categorical, and then we would work up to the actual regressions. Um, but really, so when we think about what we're doing with a lot of these models, we are inputting features or feature vectors to um, basically fit them and then use that fitted model to predict some sort of output vector or vector of y's. Um, and the reason why this is important is because we want to think, sometimes the way that we uh, encode values to put them in their input vector can really affect what our results are. And what I mean by that is, so when we have ordinal, we have categorical, and the difference really is ordinal is classified as really as categorical data, but it has a natural order. So it's stuff like, for example, if we have low income, middle income, and a high income, um, low income comes before middle income, comes before high income, or if you had like I forget there's a technical name, but the tests where it's like you have five choices and it's like, how do you feel about, blah blah blah, and then he's like mark strong dislike, dislike, neutral, like, strong like, whatever. But they all have an inherent natural order. So like you could encode this as zero, for example, or one, two, three, and four, and those values would make sense because zero is the least, correlating to strong dislike. Dislike would be one, and so on and so on. But basically, when you're encoding it that way, you are giving it a natural order. You are implying to the model, um, because of the sequential nature, um, that it has ordering. And sometimes you don't always want to do that. So you have to be careful, when you're encoding it sometimes. I mean, and take a step back, it may or may not make a difference. Sometimes it does, sometimes it doesn't. But it's just something that you want to be aware of when you're thinking about how to actually input your data. So what does that really mean for us in practice? Well, if we say we had, for example, this data frame, right? We have low, low, medium, medium, high, low, whatever, blah, blah, blah. And, if we print it out, it looks like this. That's ordinal data. So if we were going to actually encode that to put that in, as a feature column, like, in our input data, we could, use this nice function that Python has, and we can encode. We could say, okay, low is 1, medium is 2, high is 3, and then we could sort that, and it would give us low, low, medium, medium, high, all sorted, um, you know, by ordinality, I guess you could say. Um, but that's not really always what we want. We don't always want it this way. Okay. So now we've kind of touched on what it means to be ordinal and how that works, and some code that could help us actually encode that in practice. Um, and actually, yeah, okay, that's just a scalar mapper function. I just want to make sure that there wasn't a special library I had to include or anything. Yeah, so that's ordinal. So let's get into categorical. And categorical is pretty much kind of the opposite. It's categorical data with no inherent ordering, and this is actually trickier to deal with because, like we said earlier, we don't want to encode data in such a way that it gives ordering when or implies ordering when there's not. Um, so, for example, Georgia, Florida, Alabama states, those, we don't have a particular ordering when it comes to states. Not, on paper, there's not one state that's better than the others or whatever. So, we can't encode it that way. Binary classification. Yes is not necessarily better than no. And then eye color could be another example. But anyway, you guys get the idea. So there's two ways to handle it, and we touched on these a little bit in class. But one is dummy variables, and the other is one-hot encoding. And to be honest, when he was going over dummy variables and some of the stuff in class, I didn't really get it. But there's actually a difference, and there's a time when you would use one versus the other. So I'm going to try to explain this right here. But so let's take an example. I think that's always the best way. So again, we're going to create another data frame. We're going to use eye color. We're just going to say, okay, we're going to have some green, some blue, and some brown eyes. And so anyway, we want to encode this data, kind of similarly to before, but we don't really want to imply any ordering. So what we can do is we can use what are called dummy variables, or essentially a specific vector or columnar representation of these values. So okay, let me explain that a little bit better. So we have 1, 2, 3 green eyes in this set, right? So if we wanted to represent that as its own column or its own feature input, we could say that green is representative by the matrix 1, 0, 0, 0, 0, 1, 1, 0, 0. And that's representing essentially the position, that the old position that these green eyes held in the old list, for example, and then it represents there was 3 of them. So it's describing this green or green input feature just in in its own column. And since there's 3 different features, we're gonna have 3 different columns. So it makes sense. And then we can see, okay, brown. Okay, there was a brown here, so 1, 1. Brown here, so 1, 1 again. And this is representative of our new brown input feature. And you can see there's only 0 and 1, so we don't have any inherent ordering now associated with our data. So essentially, we've just kind of expanded this out and created a matrix for each of the categories, a unique matrix for each of the, or a unique, I keep calling it matrix, unique column for each of the categories. And that's the idea with dummy variables. And this way is kind of a way to get around, not giving data that doesn't have any inherent ordering. Another thing we can do, and this is kind of a different case, but say for example we have a list of unique values, and this is the difference really, is the fact that we had in this data list or data group, we had a bunch of different repeat values. So we had green, green, brown, brown. In this case, we have a unique list. We have Georgia, Florida, or Alabama, Florida, Tennessee, and if we were to go on and on, all the states, there would be 50 different, a set of different states, and each one would be unique. So in this case, we can use what's called one-hot encoding. So this is a neat library function where it will just take your data set and it will transform it into a one-hot encoded array for you, which is super nice. Saves a lot of time. Basically, let's see, Georgia would correspond to this one-hot encoding, Alabama, and notice it's just giving a 1. So if you were to have Georgia, I'm not really exactly sure how it's encoded this in here, but basically you have Georgia, Alabama, Florida, Tennessee, whatever, and then wherever that hits, it would be a 1, and then you would have this representation of Georgia, or 1 corresponds to whatever value it is out of the list. So in this way, you can represent kind of unique categories. So that was really the difference I found between them, and 2 good functions that you can use to actually, in practice, do this type of encoding. Which, I'm not really sure what kind of test questions we'll have, but this could be, really helpful just to be able to quickly do this for, an input feature for something on the exam. Okay, so let's hop into regression. So we already touched on linear, I believe, and multiple regression, and we kind of understand what those are. So this is really just a simple expansion, or a fairly basic expansion on what we already know. So now instead of just having x terms, we now have x squared terms, and that's what makes it quadratic. Just adding in those x squared terms. And this quadratic regression typically allows us to fit nonlinear relationships that are shaped like parabolas. So if we had data that looked like this, quadratic regression would typically be a pretty good choice. And one of the things I did want to touch on here, and this is very similar with cubic, but there's different. The formula looks different for the number of features that you have or dimensions that you have, and also it depends on whether or not you want to include cross terms. So, for example, if you only had one predictor variable or one input feature or whatever you want to call it, basically if you only had one x and you were trying to predict y, so let's say I don't know, you had amount of food consumed and weight of the mouse. I don't know. And that was your x was amount of food they consume over a period of time, and then y was their weight over a period of time. And let's say for whatever reason it looked like this. Well, this is the formula that we could use for that single variable case. And then if we expanded it out to 2 dimensions, so say we added another dimension, like I don't know, maybe the mouse's weight depends on how much sleep it gets. If it sleeps a lot, maybe it gets fat. I don't know. So we have 2 dimensions. We have the amount of food the mouse eats, and then the amount of sleep it gets, and those are, we're saying, are predictor variables for how much the mouse weighs. And so it would look like something like this. We have x1, x2, those are our 2 features, and we're representing it not only for just a linear case, but also the quadratic case. So we're adding in this extra term. And then let's say that there was a relationship between the amount that the mouse sleeps and then the amount of food they eat. So there was some relationship between them. Well, we can actually capture that by including cross terms, which is just the linear x1 and linear x2. So it just depends on what you're trying to capture. You can expand out this this formula to include more terms, less terms, and you can expand it to have as many features as you want. But this is just, I think, kind of a good representation of what we're actually doing here with quadratic regression, and gives a nice difference between the simplest case, expanding out the features, and then adding in cross terms. But I mean, that's just all kind of conceptual. Let's actually get down to it and see how we would implement this, or how we could implement this on the exam. So for that, I took the auto MPG data set. I mean, we should all be familiar with that at this point. And so this is what it looks like if we remember. So we've got cylinders, displacement, horsepower, weight, acceleration, model year, origin, but origin is categorical. So, I mean, at least we dropped it in the project. And then we're trying to predict this MPG. So, and then what we're doing is just for simplicity's sake, I'm only going to take three input features here, but in reality, you might want to take cylinder, displacement, horsepower, weight, acceleration, model year. If you're really wanting to train this model like we did in the project. But for simplicity, we're just going to take these 3, and we're going to say that cylinders, model, weight, and we're going to use that to predict MPG. So the first thing we want to do is we want to go through and we want to actually split up our data into a trained test set. sklearn has a great little tool or a little function called train test split, which does that for us. And then we're going to want to import the polynomial features, and this is going to, we'll see it later, but it's going to expand our feature set out to include quadratic terms, cubic terms, whatever it is that we want. And then we're going to import the linear model. So, and I'll explain why that's relevant here in a second. But so now we want to create the input features for quadratic regression. So we started out, we have these 3 input features, but we want to expand that out because now, like we said earlier, we have all of these extra terms we have to worry about. So again, Python, being the nifty little thing that it is, has a library for that. It's called polynomial features, and what we can do is we're saying, okay, we want to include terms with a degree of 2, so quadratic terms in this case, and And this is interaction only. So for whatever reason, if you only wanted the cross terms to see the interaction, so like if we go back here, if you only wanted these terms and these terms, then you would say true, and it would get rid of the actual quadratic terms and just give you the cross terms. You know why you would want that? I'm not 100% sure, but it is an option. So just be aware of that. You don't even really have to include that, to be honest, in just the degree, and it'll still do the same thing, still function. All right, so we've got our function now, and we've told it what degree we want, and now we're going to actually transform the data. So this is expanding out. So we started with 3 input features, and this is expanding that out to essentially this. And then we're saving that, and then we're going to save it as a data frame, and we're going to do like some basic, just a little bit of manipulation to get it to the data frame to come out right. So I mean, you can look into this if you want. It's just not really part of the video, or not really relevant to the video. It's just more semantics in Python. So but it is here for you. I mean, you can go through it if you want, but it works. So at the end, we're going to go through this, and we're going to get out our new input features, or our data frame of our new input features. And now that we have that, we're going to use train test split to split that into our y and x, or sorry, split that into our training test sets, and we're going to use a test size of 20% or 0.20, and we're going to keep the random state the same, so that if we do this again, it will give us the same x test, y train, and y test. If you did not include this, it would be random every time, so it would change. So now we have all of our sets that we need, and we're going to train the model, or fit the model on our x and y, or our training x and y, and then we are going to predict our test and store it as y predicted. Now we want to see what this is. So I just created this little function to output the fit, or show, I guess, how well the predicted values correlate to what the actual y's were. And then, so now we're going to import. So sklearn has this great library called metrics, and it's got a bunch of statistical scores or metrics that you can use. So you can use R2 score, mean squared error, RMS. There's like literally like, I think 30 or 40 of them that you can use. So check that out for sure. It might be helpful for the exam. But for this case, I just only imported R squared score and mean squared error. And then I just use math because we're going to have to do a square root later down the line. This is creating a basically just a list of input features, or like the number of input features, so we could make the graph come out. And then we're actually just going to graph it here. So we're showing the fit, which is the function I created. We're giving it the x value, or the list of x values. So how many basically not features, but how many rows of data do we have? There should be a data point for each. So we're just giving it a list of like 1, 2, 3, 4, so we can plot it. And then we're giving it basically the original y values, and then our predicted y values. And then we're giving it the original y's and the predicted y's, so we can calculate the R squared score, and the same thing for the mean squared error. And then the RMSE is only the square root of that, so we're just going to take the square root. So anyway, this is what it actually looks like, and it kind of looks weird the way that it's graphed out, but since there's multiple input features, it's a nonlinear output. So basically, if we take it like piece by piece, right? So this is the first set of y predicted and, so y predicted and then y actual. You can see that they're pretty close together. And so for each instance, we have a predicted and an actual, and we can see that it was spot on here. Here it was pretty far off, and it just gives you a sense of, in each case, how close we were to predicting the actual data point. And then we quantify that by these scores, right? So we can tell that there is a correlation. It's pretty good, 0.86. The actual error itself was fairly small, and then the average sorry, the mean squared error, so the average error was pretty small, and the RMSE was pretty small as well. So overall, the model performed pretty well, and that's what we're trying to kind of get out of this. So again, that was cubic regression, and for it was quadratic regression, and for cubic regression, it's pretty much the same, except now we're going to take it all the way to cubic terms, and if our data looks something like this, cubic regression would probably be a good choice, due to the nature of the type of fit that adding cube terms provides. And again, I try to include the three cases. So this is the simplest case of cubic regression. This is for two features, and this is when we add cross terms. And we can see in this case, we're actually crossing the linear term, or I guess I should just stop calling it that, but it's just the x term with the x squared term. Let's see, we're crisscrossing both of the normal x1 and x2 terms. So a lot more interactions happening. And this is where you get cross 2 and cross 3. I believe cross 2 would give you these terms, and then cross 3 would actually give you the interaction between the squares and just the regular x values. So options there as well. Interestingly enough, when we use the polynomial features, it doesn't give us the option to choose whether we want cross terms, whether we don't want cross terms, whether we want cross 2 or cross 3. I figured that would be a feature, but it doesn't look like we have the option, so just be aware of that. You are a bit limited in this case. However, you could go through and manually drop these features you don't want. That's also an option. In any case, so we're doing it. It's very similar. We're creating the polynomial features with degree 3. We're transforming to expand out our feature set. Oh, I never explained why we use linear model. So the reason why, I believe, is because all you're doing really when you're moving from linear regression to quadratic and all these others is you're just expanding the terms out to include the x squares, the cross terms, the cubes, all of that. So really, you're just increasing the feature set. But you're still the core model you're using is the linear model. It may function. I just want to say caveat here. It may function a bit differently in Scala. I'm not 100% sure how that works under the hood, but at least for Python, all we're doing is we're expanding the feature set out and we're letting the linear model do the rest. So that's why we're still using here this linear model. We're just expanding our terms we're putting in, to include these nonlinear terms. Okay. So yeah, and this is just all the semantic Python stuff. So now we have our input features. We're doing the same thing again. We're breaking our data up in a train test. Kind of copy paste from what we did above. So I'm just for sake of time, I'm going to skip this. If you have any questions, just let me know. But the interesting thing here is that for the quadratic model, we have a higher order term, but the r squared value is actually less. So if we go back up and revisit, where are you? So this is 0.86, and this is 0.84. So we actually did worse with the quadratic. Typically the higher order terms that you include, the more you're going to overfit and the higher the r squared value is going to be. But in this case, that didn't really happen. So maybe there was some sort of quadratic relationship that was captured, by the model above. So anyway, just interesting things to point out. And kind of going with the r squared being worse, so is the MSE and the RMSE. So that kind of covers quadratic and cubic. Hopefully this will be helpful to you. You can implement it in the exam, in some way, hopefully. And the final thing I want to touch on is symbolic regression. which is a little bit, I mean, it's on the same vein as cubic and quadratic, but just it's a little bit different. So um, now what we're trying to do, or the idea, the whole reason that people are so interested in symbolic regression, or some people are so interested in symbolic regression, is the fact that we can use, or we want to use data available to actually tell us what the formula should be. So, for example, I think in class, Dr. Miller, alluded to or did some derivation of it, I can't really remember, but that you can get the formula for gravity by symbolic regression. If you had the data, it would be able to regress into and output the actual formula for Newton's law of gravity. So, just to, I guess, kind of understand why that's relevant, if you were able to take just straight data and make a formula out of that, or cull out a formula, well, then you could explain a lot of the universal phenomenon that we previously haven't been able to explain. Just if you had enough data, that is. So it's pretty powerful, and there's a lot of people that are pretty interested in this. But to kind of bring it back down to the context of our class, really we're just using basic mathematical operators, like addition, subtraction, multiplication, division, even trigonometric functions, and more complex cases or exponentials. And we're trying to use those basic operators to build a more complicated equation. And we're always going to favor the smaller. So we're going to discard a large formula if a smaller one is available. For example, if x plus x squared minus 5 fit the data well, and then you had y equals x plus 1, well, and they fit the data equally well, then we're going to prefer the formula with the smaller amount of terms because it's simpler. And if they both do the same thing, then why do we need all this complication? And that's kind of the idea. You just generate a bunch of formulas and you find the ones that fit the data the best that are also the least complicated. And this is nice because it's in comparison to neural nets. You can actually understand what's going on. If you output a formula, it's much easier for everybody to understand what's actually happening behind the scenes. Whereas with neural nets, it's more or less a black box for most people. Because a lot of people don't really understand what's going on under the hood. So it's just kind of like this magic thing that outputs something usable. Anyway, so that's enough theory. Let's hop into the actual mechanics of this. So the library we're going to be using is called gplearn. This is actually a genetic algorithms library, but it can be applied for symbolic regression, among a lot of other things. So we're going to import gplearn.genetic. We're going to import the symbolic regressor. And the first thing we're going to do here, and so ideally what we want to do is take data in the real world and actually condense that down into something and see if there's a formula that comes out of it. But for the sake of this demonstration, and shamelessly, I did take this from the gplearn documentation, so feel free to go back and actually look at that. But basically what we're going to do is we're going to take an existing equation, this equation to be exact. We are going to basically create some synthetic data that goes along with this. And then we're going to try to put that data into the symbolic regressor and see if it can output that same formula. So we're just going to test, basically to see if it works. So, all right. So let's say, okay, we're going to start by creating some data. Here's our formula. And we are essentially just getting that data and we're showing the plot. So that's pretty much all that's going on here. And we're going to import check random state, and just check that data lies on this surface. I believe is what this is actually doing. And then we're going to take that data that we generated, and we're going to divide it into a training and a testing set, like we did similarly, or we did above. However, in this case, they've chosen to do it manually. So, I'm I'm not going to go into it really here, but they just, same thing as the train test. They just pretty much did it the way that they wanted to do it. And then this is really the meat of what I wanted to get into here. But so kind of in the same way we call the linear model, we're going to call symbolic regressor. There's all of these parameters that you can pick for the symbolic regressor. And you can actually input, it's not shown, but you can input the operations that you want it to use. So for example, if you only wanted to use plus and minus, or multiplication, division, or whatever the case is, you could tell it what operations you want it to include. And the generations is the number of times it's going to actually iterate through, and it's going to try to find a better equation. So you can make this 1,000, it'll run 1,000 times. But as you can see, all right, we ran it one time, we got a fit of, I'm not really sure what this unit is, but it was pretty bad. And then we did it again, we got better. And then we got worse. And then we got better. And then we got better, got worse. And anyway, so we keep iterating until we hit this stopping criteria. And as we can see here, we got down, I guess this is actually the level, oh, sorry, that's the average, and this is the individual. And then we got down below our threshold, and we're done. So we were going to go 20, but since we got down below the threshold of fitness that we want, boom, we're close enough. And to be honest with you, some of these other like features I don't quite understand, although you can kind of do your own research. And for me, I just chose to leave everything as default. But if you needed a more specific application, I'm sure you could change it. This, I believe, is the number of equations generated each time that are compared. And then this is the number of generations that you are attempting. And then this is the level of fit that you need for the algorithm to stop. Beyond that, I don't know other than random state, and this is so that it generates the same way every time. And then, so kind of like in sklearn, we're going to fit once we've trained our model. Once we've created our model, then we're going to train it on our train set. And then we are going to actually print. So this is ESTGP. So that was the model we created in the fit. So we're actually going to print out the program. And what this does is this prints out in a really weird mathematical way. It prints out the equation, essentially, the equation that best fits your data, which is really, really interesting. And so you can see that if you do all of these, so you go through and first understand in terms of what this is, and then you go through and you simplify the mathematical expression, you're going to end up back at the same equation. And you can do it if you want, but I just kind of took their word for it. But you end up back at the same equation that you started with. So, same exact thing, except we were 0.999, so, essentially the same exact thing. So anyway, just really, really neat. We were able to take, we kind of cheated a little bit because we generated our own data, but we were able to take data, and just from the data, we were able to go back to the original equation we generated from. So that's really neat, and it's very powerful. So yeah, I'm not 100% sure what we would use this for on the exam or how the question would be structured, but just in case there is something to do with it, now you have a library you can use in Python, and hopefully that should get you going on those type of questions. Okay, anyway guys, thanks. I think that's all I got, and I will see you guys in class.